All right, today we're diving into a really fascinating paper called Detection Transformer with Stable Matching. Now, this one's interesting because it zeroes in on this really subtle but super critical problem that's been holding back some of the best object detection models out there. We're talking about a fundamental instability in how they train. And the cool part? Once you solve it, you unlock some pretty serious gains in both speed and accuracy. So let's get right into it.
So here's how we're going to break this down. First, we'll get a handle on what this unstable matching problem actually is. Then, we'll dig into why it happens, what the paper calls multi-optimization paths. After that, we'll look at the really clever position-supervised solution they came up with. We'll check out the data to see if it actually works, and then wrap up with the impressive results and what it all means.
Okay, first up, the unstable matching problem. Let's get some context and define what we're talking about here. At its heart, the whole challenge this paper tackles is this deep-seated instability in how these top-tier models actually learn.
You know, models built on the detection transformer, DETR, as we all know it, they've really taken over the object detection world. I mean, they're just a dominant force. The baseline for this paper, a model named Dino, has been absolutely smashing records on benchmarks like COCO. It really shows just how powerful this end-to-end transformer-based approach can be. But for all that success, there's been this nagging issue kind of hiding in the background, you know? Something that messes with training stability and makes things less efficient. And that's exactly what this paper nails down as the unstable matching problem. So let's ask the big question, what is it exactly? Okay, so think about how DTR models work. They have a whole stack of decoder layers, right? And each layer refines the predictions. Well, the unstable matching problem happens when one specific object query, the thing responsible for finding, say, a cat, gets assigned to different cats in different layers. It's like one layer says, predict this cat, but the next layer says, no, predict that cat over there. This gives the model totally conflicting instructions. It's being told to go in two different directions at the same time. And that, as you can imagine, really slows down the whole training process.
All right, Section 2, Multi-Optimization Paths Explained. This is where we get to the root cause of the instability. The authors make a really strong case that this isn't just some random fluke. No, it comes from something much deeper, which they call the multi-optimization path problem. So let's really unpack that. So this visual really gets to the heart of the conflict. Just imagine you've got two different predictions for the exact same object. Prediction A has a fantastic bounding box, really high IOU, great positional accuracy, but the model's not very confident about what it is, so it has a low classification score. Then you have prediction B, which is the complete opposite. The model is sure it's a car, but the bounding box is kind of sloppy. The standard matching process forces the model to pick one, and that's where the whole dilemma starts.
And this table just lays out the consequences perfectly. Look at the default matching column. If prediction A gets matched, the model is told, good job, do more of that. But if prediction B gets matched, it's also told, good job, do more of that. See the problem? You've just created two totally separate optimization paths. One path is rewarding good location, the other is rewarding good classification. The one-to-one matching that's core to DTR just makes this conflict worse. Now look at stable matching. Here, only prediction A gets encouraged. If prediction B is matched, the one with the bad location, it gets no encouragement at all. This simple change forces the model down a single, consistent path that always favors positional accuracy.
Okay, Section 3, a position-supervised solution. This is all about how we actually enforce that single optimization path. And the solution the paper puts forward is, honestly, it's a really principled and beautifully straightforward approach.
The real magic here is a change to the loss function. So typically, the classification score is supervised with a simple binary target. It's either a 1 if it's a match or a 0 if it's not. The problem is this can accidentally reward the model for just being really confident about the class, even if the bounding box is all wrong. What the proposed position-supervised loss does is brilliant. It throws out that binary target and instead uses the prediction's actual positional score, its IOU, as the target. This simple swap forces the model's classification confidence to directly mirror how good its localization is. It's a really elegant solution. So, this whole idea is put into practice with two key modifications. The first one is that position-supervised loss we just talked about, which aligns confidence with accuracy. The second is something called a position-modulated cost. This one kicks in during the matching process itself. What it does is it basically penalizes predictions with sloppy bounding boxes, making it way less likely that our prediction B from before would even get picked. These two changes work together in tandem to lock the model onto that single stable optimization path.
All right, section 4, verifying stable matching. The theory sounds great, right? It's compelling. But the real question is, does it actually work in practice? Let's look at the evidence.
And this chart is pretty much the smoking gun. It's measuring what they call the unstable score, basically the percentage of times a query gets matched to different things in adjacent decoder layers. The gray bars are the original Dino model, and the blue bars are stable Dino. I mean, just look at that. The reduction in instability is massive, and it's there in every single decoder layer. It's just clear, direct proof that the solution is doing exactly what it was designed to do.
So, what's the payoff for all this stability? Well, it's exactly what you'd hope for: faster convergence and better performance. This graph plots average precision over training epochs. The stable Dino line just consistently sits above the baseline. It hits a higher AP, and it gets there in fewer epochs. It's a perfect demonstration that fixing that instability problem translates directly into a model that's just plain better and more efficient.
Okay, section 5, results and impact. And believe it or not, the paper doesn't even stop there. They introduce another cool enhancement and really push the results into new state-of-the-art territory.
So as a sort of bonus contribution, the authors came up with this idea called dense memory fusion. You can think of it like creating these smart shortcuts in the network. It takes the really rich features from the vision backbone and merges them directly with the transformer encoder's output. By feeding the decoder this richer, more complete picture, it can tap into all that powerful pre-trained knowledge right from the get-go. And the result is another nice boost to how fast the model converges.
So, the bottom line is, what do all these changes actually get you? Well, the numbers speak for themselves. On the COCO benchmark, using a ResNet 50, stable Dino gets a 1.4 AP boost over an already very strong Dino baseline, and that's in just 12 epochs. Even if you train for longer, out to 24 epochs, it's still over a full AP point ahead. And let me tell you, in this field, gains like that are a really big deal. Every little fraction of a point is a fight.
So let's wrap this up with the key takeaways. What did we learn? Well, first, this work nailed down and solved that multi-optimization path problem that was causing all the trouble in DETR. By using positional scores to guide the classification, it actually brings these advanced models more in line with the classic logic of traditional detectors, where location is king. And what's the result? Faster training, higher accuracy, and in the end, a new state-of-the-art score of 63.8 AP on the COCO test dev. Just fantastic.
And that kind of leaves us with one final big question to think about. What this research really seems to suggest is that the next big leap forward didn't come from a crazier, more complex architecture. It came from something more fundamental, a more principled, more stable way to train. So by forcing the model down this single positionally aware path, is it possible we've actually found the most stable and maybe the most efficient way to train these incredibly powerful detection transformers?